So I just updated the website to get slides for today. So if you want to follow along with the slides, they were like just updated. I just put my finishing touches on them. So I'm going to start with these slides, and we're going to try a memory diagram in slide form. So do a little bit different. Then if we have time to get to the second example, I'll go back to the overhead thing. And if anybody has opinions or feelings about which one's better, which one you learn better from, I'd love to hear it to see how to present these memory diagrams in the best way. I used to always do slide forms and in a slightly different format. With this different format, I'm trying to figure out the best way to present this. I think the slides are going to be pretty good. I'm happy with the way they came out, but you'll all be the judge of that. So let's do this. Let's get into our next memory diagram example. It's kind of a different thing to present because it's so dynamic when we're parsing things out and all that. So we're going to go through this example today. We're going to subtract 5 minus 2, or at least that's what I claim this method is going to do. I hope it does. I hope we end up getting the answers 3 printed to the screen here. But as you can see, this method is very convoluted. It's messy. It's about the worst way you could actually subtract 2 values. Very terrible code. We're using this as an example to show you how to trace through code, and we'll see if this actually does what it's supposed to do. Even with all this extra stuff, all these repeated variable names, we're going to have a whole lot of variables named x. And we want to trace through this and see exactly how that's going to work. One of the big topics today is variable scoping. What does it mean for a variable to be in scope or out of scope? Those are things we want to talk about today because those will be important next week in lab. So all of today is getting you ready for that next week lab. We lost audio on Wednesday's lecture, so I'm careful what buttons I press on here now. I'm not sure what exactly happened, but we do have audio on the next lecture, the one right after, the section C. So if you want to re-see Wednesday's lecture, go to section C to get that. It's pretty much the same exact lecture. You know, I just word things a little differently, however comes to mind when I say it. But you can check out that lecture. And that's the one that made it to YouTube. All right, so let's go through this program. I'll actually give you, is anyone chatting? I don't have any chat to catch up on, but I'll give you a second to look at this, to think about how you would go through this program. I don't want to wait too long, but at the very least, look at it and see how you would do it. And ideally, do your memory diagram as you would on a quiz. And then, I don't know, I'll give it like 1 or 2 minutes, especially if nobody's chatting, because there'll be nothing for me to do up here. Then we'll go over how to do it. All right, I do want to get through the whole thing, so I'll start going through this. I see a lot of you are working on it, so but I do want to get started. So we can get through this one and hopefully get through everything I have in mind for today. So the very first thing, we're going to set up our sheet. We're going to set up our memory diagram and draw the stack and the heap. This example doesn't happen, just happens to not use the heap, so that'll be blank for this example. But we're still going to draw the stack and heap. These are two different types of memory. The stack is where all our variables are going to go along with their values, and the heap is where everything else goes. If we have an object, right now that's array, list, map. If we have an object, it's going to go on the heap, and everything else is going on the stack. We're further going to separate the stack into name and value. The name of a variable and whatever value is stored in that particular variable. Oh, damn it. And then we're going to put some section for inputs and outputs. This is whatever's printed to the screen, and you can just kind of slap that wherever you want. We're not too picky on where that one goes. The structure of the stack, the heap, the name, value, all those columns need to be the way they're showed right there. In, out, get that wherever you can fit. I know that I'm not going to use any heap in this example, so I'm going to put in, out over by the heap, because I'm going to fill up this whole stack. This stack's going to be messy by the time this one's over. So there's going to be a lot of stuff there. In, out, just put it wherever you want. And now we have the structure. This is like where we're going to start, our starting place for our memory diagram. Stack with name and value, heap, and then a section for input, outputs. We won't use any inputs, but outputs, what's printed to the screen. Always start with the main method. When we start with the main method, first thing we do, the first two lines, create a value named x with the value 5, value y with the value value y with the value 2. So name x, value 5, name y, value 2. That you should all be very comfortable with by now. We're just declaring variables, throwing them on the stack. No big deal at that point. Next, still might be a little bit fuzzy. We've seen it a few times. But a method call. Whenever we have a method call, that's going to create what's called a stack frame. So first, we're going to put the return variable, wherever we're putting the return value of this method call, we're going to put that name on the stack, but we don't know its value quite yet. We have to go through a whole method call. We have to go through a whole stack frame to find this return value to be able to get what the value of z is going to be. So we're going to write z and just kind of hold off on the value because we got a whole call to the subtract method to do, which is going to create a stack frame, which is a solid box. Now, since this is slides and I have infinite foresight of how this is going to go because I did the whole example and then did my slides backwards, I know exactly how big to make this box. So I'm going to make the whole box and put the bottom line. When you're on your quizzes, you're not necessarily going to know how big that box should be. So just draw the top line, draw a few lines going down, a little bit. And then once you're done with that stack frame, then you can cap it off on the bottom. So just have a little bit of foresight to so you're not cramming your values and variables in on the stack. Leave your options open by not capping off the bottom right away. Stack frame. These stack frames are a big deal. We draw these as solid boxes. We write the name of the method being called, and then an arrow from the upper left corner going to the return variable where this stack frame is going to return to. Stack frames are a big deal. We draw stack frames as a solid box to indicate that this box cannot be crossed. This is a completely separate environment. When we're inside this box, we can't access anything that's outside of that box, barring things on the heap. I shouldn't say it that strongly. Barring things that are on the heap that you have a reference to. You can't access anything else on the stack that's outside of that box. We have no access to the variables x, y, and z outside of this box. No access at all. We cannot reach them. Solid boxes can't be reached. Solid box indicates a stack frame. A stack frame is created whenever we have a method call, or later in the course function calls as well. Can't cross stack frames, completely separate environments. When we enter a stack frame, we create a stack frame, we have a method call. First thing we're going to do, add the parameters, the names of the parameters inside the stack frame, and assign them the values of the arguments. So we called this with x and y. When we made this method call, we were still in the main stack frame. X and y, 5 and 2. So this results to 5 and 2. And that's what gets passed to the variables x and y that are the parameters of this method call. So quite a bit of vocab going on there. At this point in your careers, I assume you're getting comfortable with the vocab, parameter, argument, variable, especially. Calling methods, passing arguments to the parameters, things like that. If not, I could spend more time about it. Ooh, I misspelled that. I shouldn't even chat during lecture. I scheduled Nicholas for lab during lecture. Oh well. So we add those parameters to the stack, assign them the values of the arguments. What does the int 20 mean? This guy right here? We'll get to that. I assume that's the one you mean? Unless I had a typo in the slides. No. We'll get to that one. I'll have a lot to say about that one when we get to it. Next, we're going to add z equals x to the stack. Now we have our first question. We're going to ask this question a lot today. This is what I really want to talk about today is variable scoping, which means which variable is going to be accessed and which variables can be accessed. So here we have z equals x. We know we're going to put z on the stack, but it's going to be equal to x. Problem is we have two x's on the stack. Now they happen to have the same value, so we're going to get the same result anyway, but which one of these x's is going to be accessed when we ask for the value of x? Well, we can't cross a stack frame, so the answer is pretty easy here, pretty straightforward. Can't cross this solid line, so we can't access this x. No chance we can access that one. We're definitely accessing this one right here. So if they did have different values, we would be pulling this value from this x that's inside the currently executing stack frame. We're inside the subtract stack frame, so we're going to get the x that's inside that stack frame. So two different x's to choose from. We're going to choose the one inside the stack frame we're currently running in. Can't access variables outside the stack frame that's running. So that one's still not too tricky, but we are going to get to that x equals 20, which is going to throw things off a little bit. So when we're in different stack frames, we can reuse variable names all day. We have an x here, we have an x up there, we have a y here, we have a y up there, we have a z here, we have a z up there. Different stack frames, different methods, reuse variables for days. No problem here. No issue at all. Not even a consideration of an issue. The until is like 2, except it doesn't include the endpoint. So it's exclusive of this value. Other than that, it's the same as 2, where 2 is inclusive of the endpoint. Okay, now we hit our first code block. We start a loop whenever we have parentheses that do not define a method or later on a function, that's going to be a code block. And this has different scoping implications that are going to be different than a stack frame. So we create the new block for our loop. We're going to declare our looping variable I inside that block. Assign it its initial value. This is going to loop 0 until math I absolute value of y. Y inside the stack frame is 2. Same outside the stack frame, just by chance, by the way the example is set up. 2, absolute value of 2 is 2. So 0 until 2 is going to loop 0 and then 1. And then that's it. We're going to get 2 iterations of this loop. First, I equals 0, and then I equals 1. So we start with I equals 0. And then the next thing, we're going to draw a dotted line for the code block. We've seen these dotted lines. We've seen the solid lines before. We're going to explain more about the dotted line and why we use this notation. A dotted line can sometimes be crossed. So we can never cross a stack frame, never access variables outside the stack frame, but we can sometimes access variables outside a code block. So even though we're inside this loop, just intuitively, just from practicing coding for quite a while, you know that inside this loop, if I say z equals 12, you know that this z is going to be reassigned 12, even though it's outside of the code block that's currently running. Yeah?
So the code block is just the for loop?
It's just a what?
It's just the for loop in this function?
Yeah, for this case, we'll get to the if statement too. We'll have a code block inside a code block. But right now, it's just the for loop at this moment. So the green arrow will show you where we're at during the execution. We just started the for loop. Bless you. I think that was a sneeze. So dotted lines can sometimes be crossed. That's why they're dotted. They're kind of semi-permeable. But they do affect variable scope, which means it determines when a variable can be accessed and when it cannot be accessed. So it will have some rules. Once we get some more variables on the stack, I'll explain all about those rules. So variables in another, so let's talk about this scope, by the way. If the TA mentions variable scoping during the interview, this is what they're talking about, which variables can be accessed and which ones can't be accessed. I realize I haven't said that term in any previous lecture, so I want to make sure that term's out there a lot. Variable scoping. So when I say that the variables in a different stack frame can't be accessed, what I mean is that those variables are out of scope. This means we can't reach them. Those variables might as well not even exist while we're inside this stack frame. Can't access them. No questions asked. That's it. You just can't access them. Out of scope. Can't access variables across a stack frame. Can't move through that solid line. Just can't happen. Variables inside the current code block are always in scope. I'll give a strong always on that. I can't even think of an exception to that. Inside the currently running code block, the currently running, did I put innermost on this one? But once we have multiple code blocks, the innermost currently running code block, any variables declared inside that block that are inside that dashed line, always in scope. Right now, I is in scope. I don't have to look at anything else on the stack. I is in scope. I can always access I at this moment in the code. If I type I, it's that I that's being accessed. Any values that are in the current stack frame, but not in the current code block, are sometimes in scope. And the rule here, we'll see examples, we'll talk about it for a lot of this lecture. The rule here is they're in scope unless there's another variable with the same name that's already in scope. So they're in scope unless another variable with the same name is in scope. Then that variable will be in scope. So that case hasn't come up, but it will right now. We're going to talk about this x equals 20. So in this line, we're going to create another value named x, set it equal to 20, and put it on the stack. Now, as soon as we do this, we have multiple variables with the same name in the same stack frame, which is actually legal. It's generally a bad idea, but when we're talking about variable scoping, I'm going to do that to show the example. Usually you wouldn't, just don't reuse your variable names. But if we do reuse our variable names, that is okay as long as we don't reuse a variable name in the same code block. And by the way, when you're drawing your memory diagrams, good thing to remember, quick little shorthand to remember, if you ever see the word val or var, you're adding a new thing to the stack. So when I say val x, you might be tempted to think, oh, we're just setting x equal to 20. You might be tempted to think that. Since there's either val or var, val in this case, you know that you're creating a new variable on the stack, or value, as it were. So val, putting a new thing right on the bottom of the stack, wherever we are, new value goes on the stack. So if we do this on the quiz, some students are tempted to get to this line and say, there's already an x on the stack and you're redeclaring x, and they think we're writing a trick question. They'll say, this doesn't compile. QED, I'm done with the quiz. We're not going to give you, at least not on purpose, we're not going to give you code that doesn't compile on the quiz. We don't do trick questions like that. I'm not a fan of questions like that. I want to know if you understand what's going on here, not can you figure out this really tricky thing that I threw at you. It's going to compile. This definitely compiles. This code runs. It executes. It's in the examples repo. You can run it right now. You can pull up IntelliJ and run it. It works. The only difference is I changed 3 to 2 and did y less than 0 instead of calling another method, if you are looking at it. So we have multiple variables with the same name. We actually have 3 x's on the stack right now. And I can see another val x. We're going to at least have 4 x's on the stack. So we can have multiple variables with the same name as long as they're not in the same code block. If in the same code block, so right below val x of type int equals 20, if right below that I put val x of type int equals 15, that's a compilation error. I can't redeclare the same variable name in the same code block. But since I'm in a different block, everything's fine. You might argue that maybe that shouldn't be allowed, maybe not, but it is allowed. Definitely is. So if your interviewee says, can you have 2 variables with the same name in the same code block? Let me back up. If we can have 2 variables with the same name in the same stack frame, absolutely we can, as long as they're not in the same code block. Okay, this was a question. The way I set up the example on Wednesday brought up a good question. Paul and I talked about it. We actually got Ethan, the 220 instructor, involved and decided the best way to handle variables being declared inside of a for loop. The general answer is we just don't do that. In programming, we do it often. For memory diagrams on your quiz, we just won't do it. We won't ask you to answer this question. But how to represent this? We're going to have another code block, or at least another dotted line, for each iteration of the loop. So the looping variable, kind of gets its own box, the loop box. And we're going to create another box for each iteration of the loop if there's a variable declared in the loop. So we have a variable declared in the loop, so we got to think about this because it's a lecture example. Will be a little more complex than the quiz. So we're going to create a new box for every iteration of the loop, because each iteration of the loop, we do create a new value x. This came up in last week's lecture, or Wednesday's lecture. I kind of glossed over it a little bit because I didn't want to talk about it too much. I ended up just crossing out the value each time. But this will be moving forward. Paul and I will show you only this way. This is the way we're going to do it from moving forward, just to stay consistent. And for what it's worth, returning into the array, we would draw the arrow pointing to the array. I'm going to avoid that one too because that one's just confusing. But we're going to draw another box for each iteration of the loop. I'm surprised this never came up before. It actually never came up until I did that example. So we're inside the loop. We have x equals 20. We're going to hit the conditional. Y is not less than 0, so we hit our else. Oops. I already talked about all this, right? Did I? No, I didn't. So at this moment, the variable in the currently executing code block is always in scope. So this x with value 20 is in scope right now. Now this x out here that's sometimes in scope, it's no longer in scope because we have to guarantee that in the innermost block, that variable is always in scope. So if that variable is in scope and it's matching a name of a variable in a different code block, we can't access that other variable. If we use x right now, we're getting this x, which is a completely different x than this x, which is a completely different x than this x. This x we can never access inside this stack frame. This x we can't access right now while we have that x with value 20 on the stack. We're going to hit the else. We're going to put another x. We see val, either val or var, either way. You're adding to the stack. So we're adding another value to the stack. This is in another code block. We see another set of parentheses for the else. So we have another code block, which is inside this iteration of the loop, which is inside the loop block. And we have 4 x's on the stack right now. 4 x's all in memory simultaneously. So val, put a new x equals 1 on the stack. And now, holy crap, what do we do? This is the big question of this whole example. What do we do when we hit z minus equal x? We got 4 x's and 2 z's on the stack. Which ones are we going to use?
One in the innermost.
The innermost.
Yeah.
Innermost one. So we look at the bottom of the stack. What scope are we in? And that's where we start our search. We look right there, and for x, bam, we found one right away. Go us. We found an x right away. We're going to use x equals 1, which is in the innermost code block, the one that's currently executing, the one where our program pointer is currently running. We're in this code block, the one at the bottom of the stack. X equals 1, done. That's the value of x. We use the one in the innermost or currently running code block because we found x there. We don't have access to x equals 20, can't access it. X equals 5, can't access it. X equals 5 up there, can never access it because we're going across a solid line. Can't access them. We find it in the innermost block. The other ones are out of scope. Can't access them. But we do have 3 x's in the single stack frame. So you can definitely have multiple variables in the same, with the same name in the same stack frame, as long as they're in different blocks. We also have to access z. We're reassigning to z. We're subtracting 1 from it. We figured that out. And then reassigning to it. What z do we use? Okay, we look in the innermost block. I don't see any z. So we're kind of out of luck on that one. I don't see a z. So what we're going to do when we don't find a z in the innermost block is expand our search. We're going to go to the next block. We're going to search the loop. We're going to look. So inside one iteration of the loop, you can't reuse the looping variable. So that's the same scope, even though we're drawing it each iteration of the loop separately. So we look at for the loop stack, the loop, oh my goodness, the loop code block. We look in the loop code block, still no z. All right, let's expand our search. We keep searching, we keep expanding to the next block until we reach the stack frame. We got all the way to the stack frame before we found our z here. And we found our z. Z equals 5. That's the value of z we're going to use. 5 minus 1. Then we're going to reassign it back to that z. So we're going to cross this out and get 4 for our new value of z. If we didn't find that z by the time we made it to the stack frame, that's where you get compilation errors. IntelliJ and Scala is going to say, variable not found, what are you doing? Fix your code. So luckily we did, by the time we got to the stack frame, we did find that variable. So we're feeling good about our program running. Going insane right now? Do you have questions? I can slow down and answer some questions. Actually, there are questions. This is just too many x's. Hell yeah, there's too many x's. Yeah, that's the whole point of this example. There's too many x's. There are too many x's here. But if you understand what's going on with all these 4 x's, you're going to have variable scoping down pretty good. If var means you can change the variable, can be done. Val means you can't change it. Yep. Not enough x's? I don't know. I could be convinced. Not enough. Let's add more. Should have had a nested if with another x. Go insane doing the quiz. So the difficulty of the quiz will look like the difficulty of what you saw in lab or will see in lab this week, or that you can access in the lab document. Yeah.
I have a terminology question.
Mm-hmm.
In the chat, Nicholas said that those X's were shadowing, or like something that's shadowing.
Yeah.
So, like, what would you say? Like, how would you say that most interacts as, you know?
Ooh, I don't know if I remember the exact terminology. Like we're shadowing the names. So this X, I think the term is overshadows these two. That might be the terminology. But it is shadowing the variable of the outer scope. I know that's part of the terminology. I forget exactly. You have to ask Nicholas. If he wants to use that terminology and introduce it, he has to be the source of truth on it. Sorry, I don't have a better answer. Yeah.
Do we need to make another code block for the if?
Oh, can you speak up a little bit?
Yeah, can we make another code block if it goes again? So every iteration.
Can you do another code block and use the variable names again? What was that?
So we have 2 iterations right now, right?
Yeah.
Every iteration you have to make a new code block for every force.
Yes. Yeah, and that's why I only have 2 iterations, because I ran out of room on my slide. But this, we're going to see this will get crossed out, and we'll put a whole nother one here with another x equals 20. That's coming up. Yes?
Said that for like I, we'll have 0 and 1 only.
Mm-hmm.
We have 2 because y is like includes 2.
So y is 2?
Yeah.
So it's 0 until 2, but until doesn't include the endpoint. So we go like 0 to 2, but not including 2. So we just get 0 and 1. If it was 0, 2 math.absolute value of y, then we would do 0, 1, 2. Yeah, the difference between until and 2, I sometimes forget as well. It's Paul's fault. Yeah, it's Paul's fault there's so many x's. Damn it, Paul. I was going to say, Nicholas, you can't even see the slides, but he probably just downloaded them.
I'm here, Jesse.
Ah! Are you skipping lab?
No, he ended early.
Okay. All right, let's keep going on this. Nicholas, since you're here, you can answer the shadowing. Is that what you just put? Okay. So the inner variable masks the outer variables, and the outer variable is shadowed by the inner variable. Okay. You're saying we should variable shadow as much as possible? If you don't want anybody to be able to read your code, then yes. And you'll get good job security because you're the only one who can maintain your own code. right, and then we finally update z. So we found the right z, we found the right x. Z minus 1 equals 4. Cool. Then we do it again. We go around this loop one more time. So we're going to, oh yeah, we got to cross things out first. We're going to end the if else. We hit the else block, gone. That x is no longer on the stack. It doesn't exist anymore. The new bottom visually, but top conceptually of the stack is right here. X equals 20 is now back in scope, baby. Spoilers, it's never actually going to get used. That x equals 20 doesn't do anything in this program, but it's back in scope for a brief moment here. And then it's gone. So we'll cross that out. That iteration of the loop, gone. Not on the stack anymore. And we're going to update our looping variable I, increment that to 1, and then create a new block for the next iteration of the loop. Because this, what came up in the last lecture, this x is a completely different x than this x. We're redeclaring. Last time I kind of glossed over this by changing my L to an R and saying it's a variable, it can change. But this is legal. We're creating a new variable value x every iteration of the loop because we're in a slightly different environment. Not quite like a new stack frame, but a new code block each time the loop executes. So we're going to show that code block as a new code block in our stack, in our memory diagram. But we still have the overall code block because the looping variable is in its own special case. That looping variable is its own, kind of its own thing. It persists across each iteration of the loop. But anything declared in the loop, brand new variable. So we get a new x equals 20. We get a new x equals 1 inside the else block, and it's the same old story. Same old thing again. We're going to access x. We find x in the innermost block, x equals 1. Z, don't find it here, don't find it here, don't find it here. Find it right here. 4 minus equals 1. Update that to 3. Same exact story as we did on the last iteration. Cross out that iteration of the loop. Cross out the loop. The loop's done. And with your crosses, when you're crossing these out, usually I'll just go from bottom left to upper right, but it really gets messy at this point. So I'm drawing another line just to make it more clear. However you cross yours out, everything's fine. It's all fine. But all this is gone, and these will get messy. There's a lot going on, especially when the examples get more complex. A lot going on. There's going to be a lot of arrows, a lot of crossouts. That's perfectly fine. These things are messy. There's a lot going on in your computers when you run a program. We're going to show every little bit of it. So these will get messy. That's perfectly fine. Learning stuff is messy just inherently. We're okay with that. So the stack frame returns. Oh, sorry. This x of 5 is now back in scope, which also never got used. This x equals 5 was never used. This x equals 20 was never used. But they were hanging out there just to talk to us about variable scoping. So 5 is back in scope, but we don't use it. We return z, cross out our whole stack frame. The value of z is 3. Remember, we're not looking at our code to figure out our values. We just look at our memory diagram. Return z. Z is 3. Return z to z. It's okay to reuse variable names in different code blocks, especially even stack frames, especially code blocks as well. I feel bad that I missed that. That should be right down there. And then cross out the entire stack frame. That stack frame's done. It's not on the stack. It's not in memory. It's erased. Absolutely donezo. Gone. And then for the finale, print 3 to the screen. Program over. Oh shit, that's what I was supposed to do for the past hour or so. I'll have to do that still. Get paper in the lab. I Yeah, I don't have to rush home. I'll do that right after the next lecture, assuming I remember. But yeah, bring your own paper to lab just in case. But I'll get a few reams. We also have 400 students in the class, so if I miscount how many reams, I believe it's 4 for 1 week of lab. But just in case I do my math wrong or we run out of paper, people take extras or whatever, always have backup. Yeah, adding random variables to your homework. If you have homework code that looks like this, it's going to be harder to get help in office hours when it inevitably has bugs. If you're writing code like that, it's hard to write bad code that works without spending hours debugging it. All right, how are we feeling about this? Everyone feeling good about the quiz? This is my last chance to talk to you before it. Those of you who have Monday quizzes anyway. Or no, I do get one more time. We don't have any labs before lecture on Monday, but I'm going to be talking about something else anyway. Yeah.
So besides like this situation, like being redundant as an example, like are there like real code examples where it would get kind of convoluted with the dotted boxes within dotted boxes? Like what's like a real example where that would be? Like would this actually occur on a quiz?
I mean, this is a real example, but
like an efficient, you know what I mean?
Like if we did this program efficiently, there wouldn't be, I would just in the main method do 5 minus 2. There just wouldn't be much to talk about.
Right.
So we will get what I wanted, let me think of how to answer this.
Right.
So my example, I wanted the objective to be something very simple. We're just subtracting 2 values. So everybody understands what our goal is, so then we can focus on what the code is doing and how to do the memory diagram. If I had a big example that like actually does something like, I don't know, finds the closest city, pale blue dot comes to mind, it's going to be tough to even tell what we're supposed to be doing, and that's going to distract from the example. So that's the only reason I do that. But if you trace through like your task 3 or application objective, if you have that, trace through that code, it's going to get messy too. It will get messy. So this got messy artificially, but naturally, just as the objectives get more complex, you're going to have messy diagrams. Can't wait any longer to take the quiz. 5 minutes, I won't have time to do my next example, sadly. So let's just do the lecture question and get out of here.